So hello guys and welcome to another video, and this time it's going to be kind of different because now I am using a graphics tablet, or should I say my new Surface Pro 7, which I'm using in university mostly, but today I'm going to use it for a video. And the content of that video you can already see over here. And this is pretty much all the stuff that I got wrong in old videos. It's also some stuff that I just learned that I think I should put out somewhere, and I thought it fits here. And yeah, so pretty much you always learn something, and especially if you do videos like me. This channel is not even a year old, but I've already learned so much that I cannot but cringe at my old videos sometimes. So today I'm going to make things right. I'm going to say what I got wrong. I'm going to tell you how it actually works. And also disclaimer, I'm still learning. I'm in my first semester in university. What I'm studying is kind of related to what I'm doing here, but not really that much. And so I can still get things wrong. I'm pretty sure there will be at least one thing in this video that will still wrong. That is still wrong. So yeah, I don't think this is going to be the only one of those videos. But there's already a lot, as you can see from the list that I have down here. There's a lot of stuff that I want to talk about, and this is also going to be a pretty long video, because I will try to do my best to explain what exactly I said and how it's wrong and how it actually works. And it's going to involve a lot of details. So let's just start. Like half of this is related to VRMs, mostly on graphics cards. And the first thing is discrete MOSFETs exist. So here we have two graphics cards PCBs. This one here, this is my Gigabyte GTX 790 Ti WindForce, and this over here is a Asus GTX 570 DirectCU 2. Now you can see the VRM over here. This is the VCore VRM of this graphics card, and you can see you've got 1, 2, 3, 4, 5, 6, 7, 8 inductors, and each inductor has a power stage. And then you've also got the VMEM VRM over here, but that's not really interesting for now. The thing I want to say is you have this one inductor, and then you have one power stage, and that's one phase. And then over here it looks quite different, because this VCore VRM is a lot bigger, and this is actually a 6-phase. It is not a an 8-phase, because actually I got this wrong, because this is the VCore VRM. Those two phases up there, those are VMEM, which is this right here on that card. So discrete MOSFETs exist, which means you've still got your inductors, and then you have not one but 3 of these things right here. And this is still the same thing. This is still one phase for your VRM. This is the same as this right here. And so this black box here is a power stage. You can't really see it on that background. So this right there is a power stage. And originally I thought it is a MOSFET, which it is not. It includes a MOSFET. It actually includes 2 MOSFETs, but it is not a MOSFET. It is a power stage. So, because these things right here, those are MOSFETs. Those are not power stages, those are MOSFETs. And this is a power stage. So basically what a power stage is, I'm gonna, like, if this is the power stage, you have something like like I'm gonna have to. So you have a driver here, you have a high side MOSFET here, and then you have a low side MOSFET there. So that's basically how a power stage looks. Power stage. And there's also sometimes some more stuff, like if it's a smart power stage, it has some circuitry to measure current going through it and how hot it is. But basically that's a power stage. It includes two MOSFETs and a driver. And drivers, those are these things here. I'm going to get to those later. So, and basically this high side MOSFET is that thing, and this low side MOSFET is those two things right here, because this VRM is using discrete MOSFETs, not a power stage. So originally I thought each of these are also power stages, and I couldn't quite figure out why would you put 3 power stages in one phase. Well, basically because it isn't a power stage, it is discrete MOSFETs. So yeah, that's pretty much that. I specifically made this mistake in the GTX 1070 video, where the VRM for the GTX 1070 basically looked like this. It had 1 high side MOSFET, 2 low side MOSFETs. I'm also going to get to later why you sometimes have 2. And yeah, so that's pretty much the first thing that I got wrong. So power stages are not MOSFETs. So now let's get to the list and talk about the second thing. Yes, RDS on resistance and current handling is more important on low side MOSFETs. So, in some VRM videos I will be talking about RDS on resistance, and RDS on resistance basically is the resistance you have to go through when you turn on a MOSFET. And when you when you have a VRM running at 450 kHz switching frequency, you will turn that MOSFET on about 450,000 times per second. And you can already imagine probably that more RDS on also means more heat. So basically how hot a VRM gets is determined by the RDS on resistance of the low side MOSFETs, because the low side MOSFETs have to handle more current than the high side MOSFETs. So I'm gonna clean that up right here, and I'm gonna tell you what I'm talking about. So let's say we have 12 volts power from this power connector that's going in right here. You have your high side MOSFET here, and the 12 volts goes through that high side MOSFET. Then goes into the inductor, where basically that's how you produce your lower voltage. But then you also have your low side MOSFETs, which, well, how VRMs work is a different topic. That would be another video entirely. So I'm assuming you know the basics of how VRMs work. So the low side MOSFETs, there's no 12 volts power going through them like through the high side MOSFETs. What is going through the low side MOSFETs will be the output voltage of the VRM, so say 1.2 volts. And 1.2 volts in comparison to 12 volts will be 10 times the current. So those have to handle 10 times the current, and 10 times the current means the RDS on resistance has 10 times the effect of how much heat it will produce. So that's also why there are 2 sometimes. Like most of the time, if you have a graphics card or motherboard with discrete MOSFETs, you're going to be pretty much always seeing 2 low side MOSFETs, because how resistance works in electronics, so those 2 low side MOSFETs are in parallel. And if you put if you put 2 resistors in parallel, you will end up with half the resistance actively. So if you have like each of the so I think I'm going to switch to another color. So if you have 3 ohms for each of these resistors, you will end up with 1.5 ohms effectively if you put those together as one combined resistance. So that means you will only have half the heat output because your resistance is effectively halved, because only half of the current will go through each of those MOSFETs. So yeah, then there's basically two things you get from putting two low-side MOSFETs on a VRM. You get more current, because MOSFETs can only handle that much current, like they are spec'd for a certain current number, and if they go over that, they will just like blow up. So if you put two of those in parallel, you can handle double the current. Like if you have two 30 amp low side MOSFETs and put them in parallel, you can handle 60 amps per phase now. And the other thing that I've already talked about is 1/2 of the resistance. So it lowers the resistance for the low side. And the low side MOSFET is, as I've already talked about, because it has to handle 10 times the current, it will produce 10 times more heat for the same RDS on. That is also why you will often see on this specific card, if I remember correctly, the low side MOSFETs have 3.68 milliohms, which is actually quite a lot for low side MOSFETs, and then the high sides have like 4.5 milliohms or something. So you will pretty much always see that the high side MOSFET has a higher RDS on resistance than the low side MOSFETs, which is because they have to handle more current. And yeah, so pretty much high side MOSFETs just have to be fast. They have to be fast when switching on and off, and low side MOSFETs need to handle more current and have to have a smaller RDS on resistance. So basically that's it. I hope this wasn't too uncoordinated now. I hope I could explain that. So yeah, I already said that high side MOSFETs need to be fast and not have low RDS on. They can have higher RDS on because they're switching 12 volts. Yeah, so like 1.2 volts, that's just a placeholder. Replace 1.2 volts by whichever current you are, whatever voltage you're putting out with your VRM. So 1.2 volts is only a placeholder. So next thing, current ratings are always overkill. So I don't know if I ever talked about that in a video. I had several videos that I decided to not upload where I talked about this. And yeah, so pretty much what you're going to see is if you have like a card that needs, let's say, 60 amps, and you have your 6-phase V-core over here, each of those phases will have to handle 10 amps. And you will see that the low side MOSFETs are rated for something like 25 amps each, so you could basically handle 50 amps per phase, which is quite a lot compared to that you only need 60 amps as a whole. And I said something like those MOSFETs are overkill, those are basically for much more powerful graphics card, and while you probably could put a more power-hungry GPU on that without a problem, there is a reason why these current ratings are so overkill. And that is why, that is because, I think you can see that I'm not using this software for long. So, that is because current spikes are a thing. Like, if the GPU suddenly has to do something a lot different, you will like, let's make a diagram here. So, let's say those, that's time, and those are the amps that the GPU wants. So basically you're running like a benchmark, and then a very, very intensive scene comes up, and then your current will basically look like that. And that's a current spike. And that's why the current ratings for those MOSFETs are so high, because they have to handle those spikes. Otherwise, they would blow up and burn and whatever, and you would have a really, really bad day because your graphics card would probably be broken. So yeah, that's why current ratings are in quote like overkill, because you actually need that much current rating, because you could have current spikes that are very, very high, and your VRM has to handle that. So the next thing, doublers exist. I don't think I ever really talked about that, but it is something that I learned, and I think it is something very, very important also when talking about VRMs. So doublers look pretty much like this. These are not doublers, these are just drivers, like this thing right here, which is integrated in a power stage. These are those. So these are just external drivers. Like the MOSFETs are discrete ones, so you also have discrete drivers. There are discrete MOSFETs that include drivers, but on that card you have discrete drivers. So it's just that thing put onto there. And those are also dual drivers, so they can drive two phases, which is why you only have 3 of those on there and not 6. Yeah, but back to doublers. Doublers look pretty much like this. And they can also be drivers. They can also have the function of a driver. But what basically doublers do, this is your PWM controller right here. In this case, it has 6 PWM signals going out of it. But you could also, as a cost saving measure, you could put a PWM controller with only 3 PWM signals on there, and you could still get 6 phases, like 6 phases in quote marks, because it's not really actually 6 phases if you do it like this, with doublers. So basically, let's say this is a doubler, which it is not on that card, but let's assume that it is a doubler. You have 1 PWM signal from the PWM controller going in there, and what it will do is it will take 2 of your phases and will split that PWM signal in 2 different ones for 2 phases. So basically how it looks is, let's say, gonna do a diagram again. So we have time again, and let's just say these are pulses that it gives out. So let's say the green graph is the PWM controller. It gives 1 out every second, like pulse 1, 2, 3, 4, 5. And what a doubler would do is it will take that and make 2 PWM signals out of it. So it will, let's say this is the blue phase, and this is the orange phase. So what it will do is it will send pulse 1 to the blue phase, it will send pulse 2 to the orange phase, and then pulse 3 to the blue phase again, and then pulse 4 to the orange phase again, and so on. So it only sends every second PWM pulse to one phase, and then the other pulses that are getting left out go to the other phase. So effectively this cuts your switching frequency in half. So if you have like 500 kilohertz switching frequency, you get 250 kilohertz switching frequency effectively. So you can compensate for that by just doubling your switching frequency. Of course, you would need doublers that can support this, but that's a way to get around this halving of the switching frequency. And yeah, that's how you can get 6 phases out of a 3-phase PWM controller. And yeah, again, if you know how VRMs work and saw like a diagram that looks like this, well, basically, if you know how the voltage that gets put out by a VRM looks like, you will see that this is actually pretty close to an actual 6-phase VRM. So there are some trade-offs, like you get worse transient response, and of course you have more complex circuits with more failure points, and it gets more expensive. But it is a pretty effective way that if you don't have enough money to put a high-phase PWM controller on something, but you want more phases than what that controller can support. An example would be my motherboard in my main PC, the Z370 Aorus Gaming 5 from Gigabyte. That one has a PWM controller with 4 phases, and it gets made into 8 with doublers, and by pretty much this exact thing. Yeah, it's pretty close to an actual 8-phase, though a real 8-phase would be slightly better. But it is very, very close. So yeah, that's how what doublers are. Yeah, so also this is also something that I don't think I've talked about, but there can be more than one PWM controller, which is true for the graphics cards that I showed here. So this is the vCore PWM controller. This does 6 PWM signals for the 6 phases that we have on here. So right here, this is the vCore VRM of this graphics card, and it puts 6 signals into that, so each phase gets its own signal. Then you have this thing right here, that is the vMem PWM controller, and that one powers those 2 stages, which is the VRAM VRM. So the vCore powers the GPU, whereas this powers all those things. So that powers your VRAM. And yeah, originally I thought you only have one PWM controller, but as you can see here, there are 2 controllers for 2 different VRAMs. And yeah, so motherboards usually have only one PWM controller. You have like yeah, you sometimes you can find an 8-phase PWM controller, and it's and it's running it's like an 8-phase PWM controller, and 6 of those phases go to vCore, and then 2 to SoC, which is, yeah, which powers like iGPUs, and on Ryzen it powers the memory controller, I think. So yeah, motherboards often use one PWM controller, though there are motherboards that have 2. Graphics cards oftentimes have 2 PWM controllers. And yeah, that totally works. I originally thought this doesn't work, but it totally works. So this is one embarrassing thing. The INA 3221, which is found right here. That is an INA 3221. And the INA 3221 is a power monitoring chip. And originally I thought it would be this thing right here. So originally I thought it is the PWM controller for this vMem VRM right here, but it isn't. That is this. This is vMem. So yeah, that's basically the mistake I made. I thought the INA 3221 is a vMem PWM controller. It is not. It is a power monitoring chip. The INA 3221 monitors the voltage drop that occurs on those shunts right here, and there's one. And yeah, that's basically how NVIDIA's power monitoring system works. The INA 3221 got replaced for the RTX series. Those use on semiconductor parts, and also like this can monitor 3 channels, like each of those shunts. And on the newer cards they have 2 NCP something controllers that can each monitor 4 channels, because on the RTX cards they are monitoring a lot more things than on the older cards like this GTX 780 Ti. So yeah, I don't really have time to explain that one fully now. Basically, your 12 volts power goes through this shunt, and because this shunt has that is a 5 milliohm shunt, you will lose some power. Like if you have 12 volts here, you have like 11.995 volts here or something like that. And this voltage drop changes by how much current you are pulling. So the INF3221 knows that, like it knows that there is a 5 milliohm shunt there, and it knows there are 12 volts going into it. And so by how much voltage you lose going through the shunt, the INF3221 can calculate how much current is going through that shunt. And by that, the card knows how much power it is pulling. And that's basically how NVIDIA's power monitoring system works. It is pretty easy to trick, at least on the older cards. If you just swap that 5 milliohm shunt out by something else, if you put like another 5 milliohm shunt on it, and just as before, if you put 2 resistors in parallel, you get half the resistance effectively. So out of 5 you make 2.5 milliohms, and now you will and now the card will only see half the power it is actually pulling. And that's how you can increase or totally lift your power limit on older NVIDIA cards. On the newer one, it's not working anymore. You need to do a bit more stuff. But on the older cards, like GTX 600 210 series, the power monitoring system works just like this. So, next thing, also something interesting. And that thing is, you can see that on the reference version of this PCB right here. So you have your vCore VRM right here, and those are 8 phases. Like there's a PWM controller that has 8 PWM signals going into each of those phases, and the reference PCB looks slightly different. My Zotac GTX 780 Ti is a reference PCB. I don't have a picture of that right here right now, but if you watch that video, you will see that those 2 inductors here are missing. The reference board does only have 6 inductors for 8 power stages, so it is still an 8 phase. It's just that the 8 power stages are sharing 6 inductors, and yeah, that's just a thing you can do. It's like a cost saving measure basically. It is just a thing you can do. Yeah, so you don't need as much inductors as you have MOSFETs worth. So yeah, that's just basically also a thing that exists and that I wanted to throw out. So next thing, the XFX RX 480. That is a video my friend made. It is not up anymore, but I still made a mistake in that video. So the RX 480 is very, very likely a 4-phase. And in that video, like so we have the PCB right here. In that video I said that the card has a 5-phase VRM. As you can see right here, you have 5 inductors, and each of those have MOSFETs. So what I said was basically I actually wasn't really sure what it is. So in that video I said it's either a 5-phase or it's a 4+1 phase, with that one up there being the VMEM VRM powering all those memory chips again. That's not entirely true. The memory VRM is over here, and that powers your memory chips. What is over here is still not a 5-phase though. it is a 4-phase. You can see that because you can see each of those phases has one high-side MOSFET and 2 low-side MOSFET, whereas this one only has one high-side and one low-side. And no, there's not a MOSFET somewhere there. You could see it in the video. There are only 2 MOSFETs on this phase. And yeah, basically at that time I didn't know that AMD cards are actually quite different in some ways to NVIDIA cards. Because on NVIDIA cards, the VMem VRAM also powers your memory controller on the GPU. Like on here, there's a memory controller in there somewhere. On NVIDIA cards, this gets powered by the memory VRAM also. On AMD cards, this has its own memory rail. I think it's called VDDCI, I think. Yeah, I think it's VDDCI. And that's basically very likely what this one phase is right here. That is your VDDCI rail. It could also be something different. It could also be your PAX rail or your PLL rail. NVIDIA calls it one thing, AMD calls it another thing. Basically, it's just the power rail that powers your PCI Express interface. But I think your PAX rail or PLL is this one here. This little unassuming VRAM. So yeah, that's likely VDDCI, whereas this down here is vCore. So yeah, it is a 4-phase, but that one is not VMem. That is this right here. So next point. Yeah, okay, I already talked about this. If you have 2 low-side MOSFETs, you get better RDS(on) because you half it, and you get better current handling because, well, MOSFETs are in parallel. Then, another thing regarding my 780 Ti. It has a 350 watt power limit. So, this card right here. On numerous occasions, I talked about how great of an overclocker this card is, how untouchable it is by other 780 Ti's. And to be fair, there's a lot of nostalgia involved, but there are a lot of things that speak for my claim holding at least somewhat true. Because this card right here has a 350 watt power limit. The normal 780 Ti has 250 watts. That is literally 100 watts extra. That is a lot of extra power that this card can pull, specifically that this GPU can pull, because 780 Ti's, once you really overclock them, they do suck a lot of power. So yeah, that is probably one of the bigger factors why this card overclocked so well, because it literally has 100 extra watts of power. And also a nice thing is the Kingpin BIOS, which is like the extreme overclocking BIOS for the 780 Ti, like the EVGA classified Kingpin edition of the 780 Ti, that was the overclocking card for extreme overclocking, like not even water cooling, it is liquid nitrogen cooling and all those extreme things. That one had a 365 watt power limit. That's just 15 watts extra you get over the wind force. Well, to be fair, I don't think that it actually stops at 365 watts. I think it's just a number they put in there, and it can actually go way higher than that. But the fact that they even spec'd it at 365, and this one is so close to that, it's like, yeah, this is the second most powerful BIOS for the 780 Ti available. So, yeah. Then, another thing, my ASUS RX 570 Expedition 4GB. It is not good for overclocking, as are most second to flagship cards from AMD. Like you have currently you have the RX 5700 XT, and then you have the RX 5700, and that one is significantly locked down, though it is pretty much the same as the XT, it's just missing a few shaders. And yeah, AMD locked the card down, so you can't overclock it to the level of an XT. Pretty much the same is true for the RX 570, which is just an RX 580 4GB with a few shaders disabled. And yeah, one of those restrictions is a very, very aggressive power limit. So if you go to AMD's website, they will say that the RX 570 has a 150 watt TDP. So that's how much the card is designed to pull. And yeah, and the TDP works kind of different on AMD than it does on NVIDIA, because not all of those 150 watts are for GPU. It also factors in all the other things on the graphics card that consume power, like your VRAM, your memory controller, your phases, basically, yeah. But yes, so for example, my card, my RX 570, only has 85 watts for the GPU, and even if you put 50 extra % of power, which the BIOS allows you to, into the GPU, you end up at 120 watts. That's just not enough to properly overclock that card, because what you see happening is, so I validated that my card can run 1440 megahertz, which is actually pretty low, because I run a minus 25 millivolt offset. I have to decrease the stock voltage to get that high in clocks, because the power limit is so aggressive it will throttle you down into oblivion if you don't give it less voltage. And considering that my RX 570 has a very, very, very low ASIC quality, it is better than about 10% of RX 570s. And on AMD, a low ASIC quality means that your card will scale with voltage, but in order for it to scale, you have to give it the voltage, which I can't do, because I have to run minus 25 millivolts for the card to even run this clock. If I give it the like a plus 100 millivolt, I think it is, so you get 1.25 volts, yeah, it will throttle below 900 megahertz. So it is a very slow, very hot running card. And yeah, that's not great. And as of today, like 2 days ago, I tried flashing my card. I tried to flash a custom BIOS on it that gives it a power limit of 200 watts. Because I didn't want to overload the VRAM just yet. I was probably end up to give it 300 watts or something. And yeah, sadly, custom BIOSes don't work anymore on AMD cards, because AMD locked down the drivers. The drivers won't run with a non-signed custom BIOS. So yeah, and an RX 580 BIOS, 44GB version, won't install on it either, because they are incompatible. And I don't want to force it just yet, because I don't want to break my card. So that's a bummer. Like, I would really like AMD to lift those restrictions, like especially if their cards are old. The RX 570 is not the newest card anymore. It has been replaced by the RX 550, RX 5500, that is, and the 5500 XT, I think. So yeah, I would really like to see AMD lift those power restrictions, because the RX 570 is my only AMD card, and I would like to do something with AMD cards, because like yeah, I want to do something with AMD cards. I would like to do something with those. So yeah, that brings us to the last thing for today, at least the last thing that I have planned. MOSFET current ratings are not always for the voltage that you're going to put out. So if you look up the current ratings for a MOSFET, so let's say this MOSFET is rated for 30 amps. It is 30 amps at a certain voltage, which is not always the typical which is not always the typical 1.1 to 1.25 volts that most people run their GPUs at. Sometimes it's something like 1.8 volts or 14 volts. And yeah, different voltage means different amount of current being safe for the MOSFET. So I think this got into a video of mine where I said, yeah, this is this and this MOSFET and it is rated for that much current, where I actually didn't check which voltage it was rated at. Could be lucky and it could be something like 1.2 volts, and it could be unlucky and it could be something like 1.8 volts. So yeah, when I'm looking up current ratings in datasheets, or if you want to look up current ratings for MOSFETs in datasheets, or basically for everything, you have to also look at which voltage the current is rated. So yeah, and that's basically my whole list. We are at 42 minutes, or at least that's how long I'm recording audio now. I don't know how much I'm going to cut from the beginning. So yeah, that's pretty much the stuff I wanted to talk about. Yeah, as I've said, you are always learning new stuff. There's always things you didn't know that you know, and yeah, I want to make things right. I don't want to look like the I exactly know what I'm talking about, because I don't. I'm a student in my first semester, and like I'm like YouTube is just a hobby for me, and I am a PC enthusiast, and I am very, very interested in like above average level overclocking, which is why I have bought so many graphics cards, which is why I bought a whole second system which you could very, very well play games on. Yeah, I just like PC tech, I like overclocking, I like playing around with it. And yeah, it's just a hobby for me. I'm not a professional. I'm far from being a professional. If you go to Buildzoid's YouTube channel, actually hardcore overclocking, he knows so much more than I do, and he himself also says a lot of times that he's not an expert, that this is also just a hobby for him. And yeah, then he's referencing people like Der Bauer or Kingpin who actually make a living out of overclocking stuff. And yeah, so that's basically it. People make mistakes. I made a lot of them. And yeah, I like to make this video to show what I got wrong. This video is also so that if you watched it to this point, that you know what to do with what things related to overclocking and VRMs mostly. So I hope I could help you out. I hope my old videos are not that cringe anymore, no way. I've clarified what is wrong about them, and yeah, so that's basically it. Yeah, so we are at almost 45 minutes. I think we're good for now. I don't have anything more to say. So yeah, thank you for watching. If you made it this far. Yeah, and then I'm not going to beg for likes or something. You watching this video is already enough for me. So yeah, that's it for this time. Thanks for watching, and until next time, bye.